I'm very pleased to discuss with you this interesting topic of the green transformation and the competitiveness of the chemical industry in Germany. And this one doesn't work yet. Oh, now how do I get back? Here. So, this is an interesting topic, and you may first of all ask, why is this so important for Wacker? Now, there is a very important reason. Wacker Chemie in Bavaria is one of the largest consumers of electricity in Bavaria. And in my role as the head of energy and utility supply, I'm very much aware of the extremely high costs we have to spend every single day for electricity. And furthermore, I'm also aware of the direct impact of such costs for electricity on the manufacturing costs of single products coming out of Germany. So there is a very direct connection. But first, let's start with that wonderful chart here in the background. And many of you may already imagine what it is. This is a good reason for climate protection. What you see here is nothing else but the average Bavarian temperatures during the last 150 years. So starting here on the left side with rather bluish cold colors, and in the last years and decades, very warm colors, we realize we measure a temperature increase. There is a good reason to do something. And this is also a commitment of our company, of Wacker Chemie. But let's first start with a perception we have in the field of the chemical industry with regard to our production in Germany. Now, these are some perceptions, and many of you may share them. We have significant bureaucracy. We have elevated costs for labor as well as for investment. We have very high energy prices. With regards to electricity, we are roughly by a factor 2 or 3 times higher compared to our situation in America or China. We have an increasing competition, especially during the last few years, and we have already heard yesterday about the situation with a lot of competition coming from China. And we have a reasonable but challenging goal regarding the green transformation and the reduction of CO2. Now, the main question you may ask is, what can a company like Wacker, like a strong consumer of energy, do in order to help here? Now, the main message is we can significantly reduce our CO2 emissions. We have the potential to reduce our CO2 emissions basically down to 0. And that includes the direct emissions really coming from our production side, as well as indirect emissions, for example, through the purchasing and consumption of electricity. Now, we can bring them down, and that is now important, provided that there are a number of preconditions in place to make it successful. The precondition number 1 is we need more green electricity. And that's important, therefore I would like to repeat it. More means we need roughly 2 times more electricity in the year 2050 if we take the long run. And we need green electricity without a CO2 footprint. Secondly, we need a green hydrogen coming to us through a pipeline system. Number 4 is very important. We need both energies, the electricity and the hydrogen, to a very low price. And last but not least, we need to focus on the costs of labor and the cost of investment in Germany, because this is also at the moment an inhibiting factor. Now, in the coming slides, I will go into more detail and describe to you the background and the reason for the individual statements. But let's first start with a wonderful production facility in Bavaria. So this is Burghausen site in Bavaria, just located at the Austrian border. It's a wonderful site with more than 100 years of history, around 10,000 employees, more than 8,000 coming from Wacker. And yeah, what you see here is one of the largest consumers of electricity. What are we doing at Burghausen site? What is our business? Now, we have 4 different business areas. And in those business areas, we produce with a few raw materials more than 3,000 products coming out of Burghausen site. One area is silicones. So we have a wide range of silicone products. The other area is polymers, where we have important substances, for example, for the construction industry or for adhesives. Another part is biosolutions with raw materials going into the pharma industry. And there is a very important product which is called polysilicium, polysilicon. And this is a very important product in our discussion here today because the polysilicon is the main reason for our large electricity consumption. Now, what is polysilicon product? Polysilicon is looking like a stone, basically, here in a gray material, but it's very modern. It's the purest material which is man-made on Earth. So it's not something you can do easily and in a cheap way. You need a lot of energy in order to make it as clean as possible. And you need a lot of electricity for that. There are two main applications for polysilicon. One area is the production of photovoltaic modules. And the other one, and this is the very important one for Wacker, is the production of semiconductors and microchips. Within the area of microchips, Wacker has a very strong market position. So if you imagine all microchips on Earth, in your mobile phones, in your computers, in your cars, in your, not your, but in airplanes, or in electrical distribution systems, around 50% of all microchips on Earth are produced based on hyper-pure silicon coming from Wacker. And the main part of that coming from Burghausen. So it's a very interesting product, it's modern, and we do believe that we should not only try to keep such a product in Germany, we should be able to increase the production for such an important product. But you will not be surprised to hear that the cost of electricity has the major impact on the manufacturing costs of this very product. Now, Wacker is committed to help in order to prevent any kind of climate change. And this is the reason why our company has quite challenging goals, CO2 reduction goals. So our own target at Wacker is we want to bring down our CO2 emissions in all areas, direct and indirect, down to 0 by 2045. So this is our own goal, so we drive ourselves. And of course, we take a look at various options. What is the best way to do that? And here I would now like to go into the next level. When we talk about CO2 reduction, we always recommend to distinguish between two areas. The area number one is the so-called avoidable CO2 emission. That can be avoided because we have another technology in order to produce something. And there's also a so-called unavoidable CO2 emissions. Here you need to find different answers. Now, let's start with the avoidable CO2 emission. And the avoidable CO2 emission is largely connected to our demand of energy. Now, all large chemical sites basically require electricity. Oops, that was not my plan. I'm very sorry. Here, now I find it. Electricity, we all need natural gas, we all need steam and water. Let's start with the main CO2 emission here. It's the use of natural gas. Large chemical production sites use natural gas typically in order to produce steam. The steam is like the blood in our arteries. There is no chemical production site running without steam. We always need to have the appropriate temperature for our chemical reaction. So we have very modern power plants. We have a combined heat power plant here at Burghausen site. We produce the necessary amount of steam by combustion of natural gas, and we also produce a certain amount of electricity with it. So if we want to cut the CO2 emission and the major CO2 emission, we need finally to shut down our power plant. We should stop the use of natural gas. Very simple. We can do that, and we've done a lot of studies at Wacker, and we have a preferred method to do that. The preferred method to produce steam in the long run is a so-called high-temperature heat pump. It's not as small as maybe the one in front of your house. You need a football field for that, so it's really a large high temperature heat pump. But it's able to use hot water, which is recycled from the production facilities, let's say hot water with 50 degrees. And by using green electricity, we can generate steam out of it and feed our site with steam. This is an option. It works technically. It is a good variation here in order to stop our natural gas consumption and maybe in the long run then shut down our power plant, but just only leave it available as a backup system just in case that there is no wind or no sun. Regarding the steam, there is one number on that chart I also would like to explain because I think it's very important and it underlines how much commitment we have done in the last decades in order to reuse heat. When you take a look at that large site with more than 10,000 employees, and you look at the total steam demand of that site, already today, 65% is recycled steam. 65% is steam that was regenerated in the individual production facilities using the waste heat and using this waste heat in order to again bring steam back into our infrastructure system. So only the remaining 35%, they come from our power plant. And this is the portion we need then step by step to replace, for example, by high temperature heat pumps. When looking at the electricity, these are the two boxes here on the left and on the right. Of course, we have a high electricity demand. Our electricity demand in Burghausen is equivalent to roughly 850,000 households. So this is a city with far more than 1 million people. We buy a lot of electricity. We produce electricity in a certain part by our power plant. And we also produce electricity, very important, by using water. We have one of the oldest and nicest hydroelectric power plants in Bavaria. And we also keep it in a good shape. It's running since 1922. So good things remain. Now, this was the part of the avoidable CO2 emissions and a possible forecast, how we could do that. Let's now talk about the unavoidable CO2 emission. What is an unavoidable CO2 emission? For example, it may come from an individual chemical production facility, or, very important, it comes from our very specialized chemical waste incineration plant. It's very important for a large site. It's up and running, and it will be important for the next couple of years. This CO2 will be created during the incineration process, and there's now another approach, what we can do here. And here comes the hydrogen into play. I would like you to focus on the middle part here. This is a very simple chemical reaction. CO2, which we plan to filter out from the waste gas from that incineration plant, CO2 can have a nice reaction with green hydrogen. What we receive here is an organic material, like, for example, methanol. Methanol is one of the raw materials for the silicone production. So we can, at one side, stop the emission of CO2, and secondly, have a kind of reuse and regeneration of an organic substance. And this is where the green hydrogen has an important role. Secondly, of course, we would like to replace the gray hydrogen which we have today. Today we produce hydrogen in a normal steam reformer plant with natural gas, again causing CO2. And of course this hydrogen, the gray hydrogen, can then be replaced by green hydrogen coming to us through a pipeline system. So therefore the hydrogen has also a direct impact on the reduction of CO2 on a large chemical site. In the first couple of years, we strongly expect that there will be mainly a chemical use of hydrogen. We cannot easily imagine that it's so interesting to use it for energetic purposes, because if you use the hydrogen and just burn it in order to create heat, it needs to be available in very large amounts and it needs to be extremely cheap. We're not sure how quick that progress will happen. Maybe in the 40s or 50s, that could be a nice idea to take a look at, but at the beginning, we as a company will probably focus here on the chemical use. And this is also a reason why Wacker is engaged in a project that brings a nice pipeline connection to Bavaria, to Burghausen. If everything is fine, it will maybe start in 2032 or 33. So that is at the moment the forecast. This is a nice chart, and I want only to explain a very important topic of it. I mentioned earlier that we need more electricity, 2 times more electricity. This is a nice study that had been carried out by the FFE in Munich. And the question of the FFE to all the large chemical companies in our neighborhood, in the Chem Delta Bavaria, was how much green electricity will you require and how much hydrogen will you require if you follow your plans to bring CO2 emissions down to 0 in the next 20 to 30 years. And each company like Wacker reported the data back to FFE and they summarized it. And the yellow boxes here, oops, I'm not yet super familiar with that wonderful thing. So, but now, the yellow boxes here, they show the demand for electricity. And the thickness here of that box indicates the amount the total Chem Delta Bavaria requires. So the thickness here is our today's demand, and here the thickness in 2050 is roughly the double size, the double thickness. So this is the development of the energy requirement in terms of electricity. You also see the consumption of natural gas here. This is the gray, thicker one that goes down and shrinks to almost 0 in 2050. And you see here a bright blue color. This is the future green hydrogen demand. So what I want to say is we increase the electricity demand by factor 2 is not just a rough guess. It's quite a good study which was carried out in a good quality by the FFE. This is the background of that study. So it's something we need to take care about. Now the next picture is some interesting one because it underlines that Wacker has more than 100 years of experience. And here on the left side, you can see our old hydroelectric power plant commissioned in 1922. And you can see our old raw material, it was carbide. It was the main substance in order to generate organic substances. And we've already gone through quite a difficult change period. That was in 1950, 1960, because our chemical production site required more electricity, but the hydroelectric power plant was used up. We couldn't get more. We wanted more reliable and cheap electricity. And secondly, we realized, well, the carbide is not the raw material any longer for our competitiveness. So we asked, of course, for the petroleum hydrocarbon chemistry coming to our site. And there were 2 very important governmental decisions which were extremely helpful. Number 1 was the build-up of many power plants, fossil power plants as well as nuclear power plants, with a clear subsidy coming from Germany and Bavaria, offering a lot of electricity to us at a low price for many, many years. And the second one was also very interesting. It was the decision to build a pipeline. This is the TAL pipeline, the Transalpine Leitung. That pipeline was a pipeline from Trieste in Italy, from Trieste, Italy to Austria, crossing the Alps, coming into Bavaria and ending in the first place at Burghausen site, bringing all petroleum hydrocarbons to us. Apparently, it was realized in just 3 to 4 years. And the interesting thing is, because I now went into the data and the newspapers, is the whole pipeline was already built and set up. And at that moment, everything was already in our ground. At that moment, there was finally the approval from the Bavarian government to build the pipeline, after the pipeline was already in the ground. What did they do? And that is a nice pragmatic situation. And maybe we need to open up sometimes again our head and think what we can do. The government said, you can do that, but we will allocate 2 or 3 good engineers from our authority department to your construction site. And they join you during the entire construction. And they were approving every next single kilometer they were doing, step by step on the construction site. And that was very quick. It was in line with authority requirements. And finally, the Bavarian government just said, okay, let's summarize all these hundreds of single mini approvals during the construction. Let's get started. And there were 2 very important things. And there were a lot of investments coming in our region, a lot of investments, not only at Wacker, after those 2 steps. And this is what we also basically recommend for the future. We need to have a green electricity price for a long time, and we also need to have a low hydrogen price and a good supply situation through a pipeline system. So bringing everything into short words, I think our competitiveness made in Germany will be good if we can bring our manufacturing prices in Germany down. We need to bring our prices down, not up. And we need a good strategy from the governmental point of view, from our point of view. That means subsidies for the green electricity and hydrogen. Regarding electricity, we recommend a price of 4 cents per kilowatt hour. In the field of hydrogen, we ask for a green hydrogen price which is equal or lower than today's fossil-based hydrogen. And we also ask for individual investment promotions for such projects who significantly reduce CO2 emissions, like, for example, large heat pumps. We also need to expand the infrastructure. This is true now for the pipeline system hydrogen. It is also true for an additional electricity connection of the Chem Delta Bavaria. This is a planned additional 380 kilowatt line coming to our region. Yeah, and last but not least, we think we should do something. We should not wait and see, but we should do something. We should take decisions. We should simplify something. And actually, I like here that nice saying in the Leopoldina, nunquam ociosus, which means don't be idle, be active. Thank you very much.
That is very company specific. And I will try to give you a more broad view of the role of the chemical industry. And we're going to ask the question, basically, how we are going to embark on a change, allowing us to step away from fossil resources. Yeah? And that focuses specifically on the question of carbon-based products, because a lot of the products that we produce are carbon-based, basically. We heard about an exemption, very important. And I will focus on challenges and opportunities. Yeah. Now, what are we going to embark on for the next 20 minutes? Let's first take a global perspective and look at chemistry as an enabler. And then I would like to look at the chemistry as a whole, asking the question, why are we called the workhorse of the manufacturing sector? And then specifically, we're going to look into carbon-based value chains with the question of coupling of energy and matter. And I promise you it's not going to be alchemy that we're going to do there, but it's a real chemistry that happens on a daily basis. And what is, of course, important when we're looking of coupling of energy and matter is to understand the energy system and also the energy market, particularly with regards to renewables. Yeah? And the last part is going to be about matter, and that is basically carbon that we will try to have to keep in the loop in the future. Okay, let's take a global perspective, and I'm happy that we have the director of the Potsdam Institute here, because I'm using one of the graphics that you recently published. Yeah? And this is a serious graphic, and what I would like to say, first of all, I like it as a chemist, because you can basically argue that it takes a view of Earth as a chemical reactor. And we're trying to operate this reactor safely. And this is what we do in the chemical industry. All of our operations are designed to be safe. Yeah? And now what basically from an intellectual point of view, it's very interesting to see what has been established here is a very simple tool to identify the areas where we're entering an unsafe or critical zone. Yeah? I think this is a great system, because with this system, one can act on a targeted way and basically try to compensate what has gone wrong in the past, so to say. And these breach boundaries show worsening trends. For some, we are already in a higher risk zone. Yeah? And for me, and I think for many of us in the room, we have to ask the question, can the chemical industry be an enabler to basically mitigate those damages? And I think it can. We heard about technologies that can enable a pathway for climate change mitigation. Low carbon processes are one of the examples, or electrification of the chemical industry. Sustainable resource use, circularity is one of the essential points here. Catalysis innovation for lowering the specific energy demand. Pollution reduction does not only concern the industry, but it's also about societal change. How do we deal with our daily products? Land system change and biodiversity. Here also the chemical industry can make an impact, and of course also emission of novel identities, so to say, so the eternal chemicals. Yeah, that's also something where we need to look for substitutes. Yeah. Now, starting from this point, basically, let's take a look at the economic impact and the societal impact of the chemical industry, and let's put this word of workhorse basically in the middle. Yeah. So if we look at, let's say, the top sectors, one can really say that with 500 billion turnover annually within the EU, the chemical industry is an economic powerhouse. Yeah. But it's also an innovation engine, and not only drives innovation in the chemical industry, but of all of the other sectors with the solutions that we provide. And it's also an important employment and industrial backbone. You can say that 3 million jobs directly associated to the chemical industry basically represent a large part of European employment. Yeah. And it's also important to understand that the chemical industry plays a major role in all of the supply chains that we have within the industry. And this is basically also illustrated here, because the chemical industry supplies essential advanced materials to all of the other sectors. Yeah? And I will focus now the rest of my talk on carbon-based products. And why is that? Because 70% of the products basically that come to the market are carbon-based. Yeah. And that's kind of like one of the important issues here. And they are the starting point for countless value chains and enable, let's say, lots of technologies in the different sectors. Now, in terms of added value, and that's also very important to understand, and that's also why I made a critical remark about, let's say, letting go energy-intensive industries. It is important to understand that if we calculate value of output versus minus value of inputs and calculate the monetary added value, this is where a lot of monetary added value is created and is then diverted to the other industries. Yeah. And letting that value go basically means also putting the other industries regionally under a lot of pressure. Yeah. Now, I spoke about the total employees. If you see here, basically it's also number 2 within the employers' landscape of Europe. Yeah. That's also important to understand that a lot of the jobs basically are important in Europe on the chemical industry. Now, from this positioning, let's take a step into carbon-based value chains, and let's look into the coupling of energy and matter. So these are the chemical changes, chemical sales here. I already said that 70% on a monetary basis by value is carbon-based. Yeah? The output, our outputs are carbon-based, and that basically means petrochemicals, classical petrochemicals, polymers, and specialty organicals. Yeah. And basically, this is also why I will focus the talk, let's say, on this major fraction, because here the question is also how can we step away from the fossil sources. And it is important to understand here that the energy intensity of the chemical industry is the highest of all of the industries that we have within Europe. Yeah. And this comes basically, let's say, of course, from the fact that how do we allocate energy intensity? And we heard it before. Basically, we consume a massive amount of gas. So 33% of the raw materials that we consume are gas-based, and also 17% of hydrocarbons. And here basically comes the electricity, and then comes all the rest, inorganics, other products, a bit of coal. Now, what is important to understand is that, of course, it's right that we use the gas and part of the petrochemical products to generate energy. But part of these products are also used as an entry point into the carbon-based value chains. That's also very important to understand. And this is the coupling of energy and matter. Yeah? And here also the value creation through synthesis starts. And this is basically where we need energy. So I'm going to bug you with a little bit of chemistry here. So just to illustrate. So we start with a very unreactive molecule, that's ethane. It's a typical starting point in an ethane cracker, for instance. Now, in order to convert this ethane into a reactive intermediate, we need to invest energy. That is illustrated here on a Gibbs energy scale. Yeah? And this is basically where the coupling of energy and matter happens. If we go to a more reactive intermediate, we need to invest more energy, that's acetylene. Yeah? And that basically illustrates to you the more reactive we are, the more energy we need to invest. But these are only the intermediates. We basically then bring them into products where we basically divert part of the energy which is dissipated. This graph is also to illustrate for you, if we start from carbon dioxide, we basically need to step up a lot on the energy scale. Yeah? And that's basically puts especially carbon dioxide-based processes under a lot of stress with regards to the cost scenarios. What is important to understand also is that energy efficiency due to the high energy intensity has always been a topic that the chemical industry has worked on. And you can see here basically that the specific energy consumption has systematically been brought down through new technologies and innovations. Yeah? And the productivity index has basically also risen. Yeah? So it's a constant topic basically which allows us to be competitive on a global scale. Now, when we take a step back and ask ourselves, in regions where we have cheap access to energy, whether it's fossil-based or renewable-based, I do not want to discuss at this moment, but this is basically a picture which will mainly be fossil-based. And again, we're taking a look at ethylene, and most of that is produced in ethane crackers. You can easily see that our cost position in Europe, if we compare it against North America and Middle East, where ethane is abundant and natural gas is cheap, is not very good. Yeah, so we have a hard time and we struggle. And that is also basically demonstrated in the production growth from 2013 to 2033. This is a factor which is basically a result of our damaged cost position. Now, in order to green our production, electrification is one of the big hopes. And what I would like to illustrate to you are some of the challenges that I see with the current energy system and the current energy market. So we want to step from a conventional industry which takes fossil resources and basically uses them and turns them into products, into an industry which is electrified, uses sustainable resources, electric energy, new processes through new technologies, and then we basically have those low carbon products which we hope that, and we hope that we also find a market that is stimulated. Now, let's take a look at our supply systems, yeah, just to illustrate some of the challenges that we have. So this is, let's say, a simplified graphic of the national grid that we have for gas. So this grid diverts 844 terawatt hours per year. 61% of this gas is used by the industry. The grid length is 1.5 times to the moon. Okay? So with this grid, and the grid volume is 24 billion cubic meters, and we have an additional storage capacity of the same size. So the grid itself stores gas, but we have additional storage capacity. And that's an elegant coupling because you have a grid that stores energy. You only need a little bit of additional storage energy and you can basically balance that grid. Very important, the investment since 2018 into our grid has almost been flat. So we maintain the grid and we're fine with it, okay? Let's take a look at the national electricity supply. So this particularly does not store much energy, but it's a grid that needs to be fed. The demand here is around 460 terawatt hours. So it's, let's say, roughly half of what we supply via gas. Now, what's the size? It's 5 times Earth to Moon. It's a much larger grid that we basically have to supply. And now comes the big frustration. We see that since 2018, we have an exponential increase in investment into our grid. And this exponential increase is largely driven by renewables that we feed into this grid. And it's not going to end here. We have roughly 1,500 workdays till 2030, where the energy efficiency legislation of the EU steps in. And you can see that there's a large imbalance in fossil energy carriers that we divert versus renewable energy carriers. This is going to be a burden for industry and a burden for society. Now there's another burden, and this is particularly one which is basically hitting industry. You can see here the market price for electricity. And we have a supply situation where under, let's say, certain circumstances, our prices start to skyrocket. And that is because we do not at present have a grid situation where we are able to compensate for the input of renewable energy via other sources that can keep the prices in a predictable region. And this is why we have those skyrocketing events where the energy prices basically shoot through the ceiling, and where we also, with our national grid situation, cause a lot of frustration in the whole European energy market, which is a coupled market. Yeah? And this is an investment preventing situation. So it's clear that any investor will basically ask himself, if I put my production facilities in such an environment, is this going to be sustainable for my investment? And I don't want to give an answer here, but I think this price volatility and market fragmentation basically is not the same one. Yeah? Now, let's take a look at carbon dioxide and pretend that we want to sustainably produce chemicals from carbon dioxide. And let's just take a look at the business cases. I think technology-wise, this is not magic. Yeah? Most of the technologies that went into this study of Wacker Chemie, with whom I collaborate, are on a very high TRL level. So they could be implemented within a very short time. Now, the issue here is that there are 2 cost drivers, and one is basically the sustainable hydrogen, and the other one is basically the green electricity. And you can see that those bars basically add up, and they basically skyrocket. Now what's this red line? This red line is the spot price of ethylene in the European market averaged for the last 8 months. And you can see that we're a factor of 3 basically for the best technologies away from being commercially attractive. And this is basically why most of the CCU cases don't work unless they're subsidized. Okay, the last part is going to be about keeping carbon in the loop. And we have already seen that keeping carbon in the loop via the conversion of CO2 is a tough cookie. Now, CO2 we have discussed, the business case is tough. Biomass I will not discuss. I think we have very solid analysis on availability and pricing from the Helmholtz Society, from other sources. Yeah? We believe in a future where biomass may play a role, but I think also looking at, let's say, boundaries of our planetary system, we need to take care about our plastic waste. And we need to basically bring our plastic waste back into the system and valorize the carbon. Now, what is the frustration there? There has been a lot of discussion on what is the right technology. And my personal view is that much too early we stepped into the process of regulation without really being technology open and asking the question, what's the right combination of technologies that allows us to operate on a sensible basis? And particularly here we have a building block which has not been valorized, I think to a large enough extent, and that's syngas. And why is syngas so important? If we go to mechanical recycling, there are special properties of that polymer that we basically need to bring it back via mechanical recycling. We need a thermoplastic, a so-called thermoplastic. And with the current product portfolio of polymer being emitted to the market, we can only recycle, most optimistically, 15 to 20% of the polymers. And we cannot put a thermoplastic in any application. That's one of the things. So we need the other technologies like solvent-based recycling, solvolysis, and particularly these technologies, pyrolysis and gasification, are super important for the wastes which are hard to deal with. And that's mixed plastic waste, and that is the largest fraction of plastic waste that we have to deal with. And there's an upside to gasification. We could also basically use this for the workup of landfill. And it couples also very well with hard to deal with biomass. So there's lots of upsides for gasification, I believe. And there's a very good study from a colleague from Shell called Plastic Recycling Stripped Naked. You directly find it for download with a very solid cost analysis also. Now, I want to use some data of Jean-Paul, and that is particularly here. And pyrolysis and gasification have received lots of criticism, and that is due to the low recovery yields that you get here. Yeah? So not every carbon is recovered. So it's around, at best, 60%, let's say. But the energy intensity is also low. And with a product, a raw material that's hard to deal with, I think this is a good compromise. And if you add all of these technologies basically together, you can come up to recycle rates predicted to be around 60 to 70%. And I think this is a potential way to go. But what we need for this is technology openness. So what I would like to stop with are some proposed action points. I think we need to keep the engine running. Chemical industry is important for our industrial value chains. It's an important motor. It's important for Europe's strategic autonomy, and it will reduce the dependence on imports. I think we need to think about how can we create growth frameworks that leave the industry competitive, that foster investment, that foster innovation into sustainable technologies, particularly low-carbon technologies. How do we basically tailor our circular economy practices? How do we participate in global value chains? I think what is very urgent is to think about what do we do with our energy market? How can we adapt our energy market, particularly when it comes to renewable energy, that basically allow a cost-competitive delivery of energy to chemical sites in this, but also to other users, so that basically Europe remains an attractive place to produce. And finally, for the circular carbon frameworks, I think technology openness is very essential. Yeah? So we need to allow different pathways like CCU. We need to look at available biogenic feedstocks. But what's particularly important for me are those advanced recycling cascades, which basically allow us to play the whole piano and basically foster the recycling of carbon. And with this, I would like to end, and I hope for stimulating discussion.